we have seen what happens to the single degree of freedom system, how exactly it reacts to a force which is external to the system and is varying harmonically. We have obtained a solution of that particular spring mass system's displacement. We have also seen that how exactly it varies with varying frequency of excitation. And in the last class we have talked about base excitation, that is when base is having certain displacement, how exactly a spring mass system which is mounted onto it, how the mass of that is going to react to that base excitation, and how much amount of force is transferred to the base if a single degree of freedom system is mounted on a base and that single degree of freedom system is applied with harmonic excitation. These are things that we already have seen. Now we are going to have a look at one another aspect in this particular class. So what we are doing is, after completing solution of a single degree of freedom system to harmonic excitation, so we are kind of having a look at all those probable and quite frequently encountered scenarios where we are going to need this uh, whatever that we have done before, this response of single degree of freedom system to harmonic excitation. And we are considering peculiar cases of which we have seen the base excitation. We also have seen how much amount of force gets transmitted to the base. So these are some certain things which are very important and we quite frequently encounter them. And now we are going to consider one more such a scene which is uh, quite oftenly encountered in mechanical engineer's life, and you should be aware of how exactly that fits into this forced vibration of single degree of freedom system when force is harmonic in nature, and how to solve that and what happens to the solution. So what exactly that solution tries to tell us. So these are certain things that we need to know, and that is something that we'll be doing it. And that frequently encountered aspect is that of rotating imbalance. Okay, so assume that there is a machine. Okay, it can be let's say a pump which is operating on a floor, and that has been approximated in this sense, which is the most crude approximation. It can be a pump or even the washing machine which is there sitting in your house right now. Okay, so it has got rotating parts into it. Okay, so let's say m is mass, and that mass has got certain parts which are rotating. Okay, not entire mass is rotating, but part of mass is rotating inside. Okay, and let there be k, which is the stiffness of the spring. Let the damping coefficient be equal to c. Okay, and now I'm going to make a statement that whatever mass that is rotating inside this, okay, most of it is balanced. However, a small part of that mass is still unbalanced. Okay, and that is let's say over here, which is slightly away from the axis of rotation. Let's say that this is the axis of rotation which is perpendicular to this plane on which I am drawing it. Okay, and this is the mass which is displaced with respect to this axis of rotation by e units. Okay, so it is e units away from axis of rotation, and this mass is small m. This is small m and it is e units away. Okay, this small m is part of big M. Okay, big M is the mass of total machine. Okay, part of that mass is rotating, part of that rotating mass is not balanced, and that unbalanced mass is causing certain problem, and that we are going to see in the today's class. Okay, so what will happen if such unbalanced mass is there in the system? Okay, what will be its effect on the system? Will it cause this certain impact on this capital M? Okay, you already have seen. So most of the times when machine is installed, we try to carry out this particular test whether everything is balanced inside it. If there is an unbalanced mass, then machine is going to show us vibrations. So what we do is we put certain vibration measuring instrument into it onto it, and we try to see how much vibrations are there, and depending on that we try to make a comment whether the mass inside is balanced or not balanced. Okay, you might have even seen it happening in your own houses. If you have seen a washing machine installation the very first time, the washing machine when it is installed, that time they carry out a one test by putting a glass of water on that washing machine, by putting that washing machine on. So if washing machine is well balanced, then the glass of water stays over there and water does not spill out of it. Okay. Which is essentially means that everything is balanced. However, if it is not balanced, then what happens, that we all are aware of. Okay, so let's try to derive that mathematically in today's class. Okay, so we have got this small m which is now unbalanced, and we are interested in knowing what is the effect of it. And this is the axis which is perpendicular to the plane, and the rotating parts which are there, they are rotating in clockwise direction with angular velocity omega. Okay, this time this angular velocity omega is that of the rotating parts. Okay, so when angular velocity inside this capital M, when whatever rotating parts are there, they are rotating with omega, then what is going to happen, because of this mass which is not unbalanced, now this which is not balanced, which is in the unbalanced stage, now because of that you already know that there will be certain force which will be coming onto the system, okay, which is a centrifugal force, and that centrifugal force will be equal to m e omega square, where e is the radius of this rotation. So this circle on which it is rotating, on that which is tracing the rotating path of this small m. Okay, and it is the radius of that circle. So it is telling that this small m is e units away from center of rotation, and this omega is speed of rotation, angular speed of rotation, or it's a circular frequency. Okay, so now our system is like this. Let me draw it over here. This is axis of rotation, and we have mass over here, and from that mass this much amount of force is acting, which is m e omega square. Now what will be this angle with which it is inclined to the x-axis? Okay, that angle will be equal to nothing but omega t. Okay, as t progresses, this angle is going to change. Okay, so we are assuming that right in the beginning this mass was over here. Okay, otherwise if mass was over here right in the beginning when time was equal to 0, that is over here, okay, when time is equal to 0, then you would have added so this, then you would have kind of reduced that theta from this one. Okay, so this much amount of theta you would have reduced, not this much, I'm so sorry, it will be this much, this will be the theta, and you would have subtracted that angle from omega t, and that would be the total angle. But time varying part is this one, omega t, right? This is time invariant part. Okay, so now you know the angle which I'll be considering as omega t itself. I won't be considering it as omega t minus theta. Okay, so now this is the force which is acting at angle omega t, and it is m e omega square. You can obviously find out two components of that force. One will be directed in the vertical direction, and the other one will be along the horizontal direction. Okay, so what will be that component which will be along the vertical direction? It will be equal to m e omega square sine of omega t, whereas that component which is acting in the horizontal direction will be equal to m e omega square cosine of omega t. Now I am making a statement over here that we are neglecting the horizontal component of it. We are not at all going to take care of the horizontal force, which is unbalanced force. Okay, now why I am saying that we are not going to take care of it, because I am assuming that either this mass is in the guide, okay, constrained in this fashion. Okay, So as such, whatever happens in this horizontal direction, uh, that is something that we are not going to take care of, because that is not going to vary dynamically. There are guides over here, and I mean, it is going to vary dynamically, but we are not going to consider it because guides are there, and that's why they are not going to allow motion of the mass in this direction. Okay, so motion of mass in a horizontal direction is something that we are neglecting. Or you can always think of it that horizontal component is balanced. Okay, only vertical component is not balanced. So that's why we are going to consider this part itself. Okay, and another and very important reason is that we are assuming that K and C are in this direction, the vertical direction. That's why we are considering only vertical component. Okay, so now let's try to see what happens to it. So now we have this system, capital M, and it is acted upon by a force m e omega square sine omega t, and these are spring and damper elements, right? So this rotating imbalance which is there in this system has been now translated in this way. Okay, so what you have done is you have taken care of equivalent force which is coming because of that rotating unbalanced mass. Okay, so let me try to write down equation of motion for this one. Now it is pretty straightforward, you are already aware of it. Okay, however, I'll still write it down for you, and it is equal to mx double dot plus cx dot plus kx equal to m e omega square sine omega t. Okay, now in this one, this capital M is the total mass of machine, which also includes small m. This is very essential for you to know. The small m also performs vertical motion. Okay, while rotating about that center of rotation, it is also performing vertical motion because of this force which is coming over here. Okay, so this force, which is the result of that unbalanced mass, is causing this entire capital M to vibrate in the vertical direction. And what is the displacement of that vibration? That is x, right? This is what is the displacement which is over here. And by writing down this equation, we have been able to formulate that how exactly that x is going to vary because of this one, okay, which this force which is coming onto the system. Okay, now you know how to solve it. It is pretty straightforward. This you can think of it as the same force which we have seen before. Okay, so what it will be, it will be equal to so x, how can you find out that? It will have two components. One will be the transient part and another will be the steady state part. Transient part, as always, we are not going to have a look at, and we are going to study only the steady state part. And you already know that how exactly the steady state part, that expression of that part is. It is amplitude times sine of omega t minus phi, right? This is sine of omega t, and you are going to have a phase lag that will be by phi. Or you can write down in more uh, typical fashion in this way: omega t minus pi by 2 minus phi, right? So this sine omega t itself is cosine omega t minus pi by 2, right? Okay, so now you have defined this x. What is capital X? Which is the amplitude of vibration of this mass in the vertical direction. So by what amplitude this mass is vibrating in the vertical direction in the steady state condition is what is this x. Okay, so you know that it is equal to amplitude of force which is coming onto it, okay, which we call as f0, divided by k, which is the stiffness of the system, divided by under root 1 minus r square square plus 2 xi r square Okay, so in this one, this f0 that I just now have talked about is equal to amplitude of force which is coming onto the system. What is f0? In this case, it is equal to m e omega square. Okay, it is very interesting condition that f0, which is the force, that force amplitude, that itself depends on what is rotating speed. Okay, so whatever that we have seen so far, in those cases f0 was a constant number, okay, and which was not varying with varying uh, forcing frequency. Whereas in this case, that forcing frequency, which is this omega t, omega appearing in this omega t term, that forcing frequency appears in the amplitude of force itself. Okay, so this is frequency dependent forcing term. So it's not only varying with time because of that frequency, but its amplitude also changes with the frequency. Okay, so let's try to derive how exactly this x comes out to be. Okay, so it is equal to m e omega square divided by k divided by 1 minus r square square plus 2 xi r the whole square. Right, now let's have a look at this term. Okay, let me rearrange it a bit. Okay, so it is m e omega square divided by k. Now what I'll do is I will multiply by m and divide by m. Okay, and I'll rewrite it in this fashion: small m e divided by capital M into omega square into capital M divided by capital K. Now this capital M divided by capital K is what is omega n square, that is square of natural frequency. Okay, this is capital M over here. Okay, total mass of the system. Okay, then that will give you omega n square. If you divide that capital M by K, what you will get is 1 over omega n square, rather, because omega n square is square root of omega n is square root of K by M. Okay, so this term comes out to be equal to small m e divided by capital M into omega square into 1 over omega n square. Okay, and this one, which is omega square divided by omega n square, is nothing but r square. Okay, so which is the ratio of omega with respect to omega n square of that ratio. Okay, is what we are getting over here. So which essentially tells us that this is equal to m e divided by capital M into r square. This is the amplitude. This is the numerator of the amplitude that we are getting. Okay, so if I write it further, I'll get it this way. So what I'll be doing is I'll be putting this value in this equation. Okay, so I am getting it in this way: capital M, small m e divided by capital M into r square divided by under root 1 minus r square square plus 2 xi r whole square. Okay, now this set of terms I'll bring over here on the other side of this sign. Okay, so if I do so, what I get is I get this non-dimensional number capital M times capital X divided by small m e. This is equal to r square divided by under root 1 minus r square square plus 2 xi r the whole square. Okay, now let's have a look at this term which we have obtained. This is firstly a non-dimensional term. It doesn't have any dimension. Okay, m and m dimensions of m and m get cancelled, dimension of x and e gets cancelled. So it tells you this x is amplitude of m, so m times amplitude of its vibration, so total mass times amplitude of its vibration, so that in comparison with the unbalanced mass times its distance from axis of rotation. Okay, E is distance of the small m from the axis of rotation. So this multiplication, with respect to this multiplication, where is this one? Okay, so because of this unbalance that we see over here, so how much amount of displacement for this much amount of m that we are getting, displacement amplitude is what is we are plotting, we are writing over here. Okay, now what I'll do is I'll try to plot it. Okay, and we'll try to see how exactly it looks like. So on y-axis we have capital M times capital X divided by small m times small e. It is this non-dimensional parameter. And on x-axis we have r, not r square, r it is. Okay, now let me mark certain peculiar points over here, as we already have done before in previous cases. Okay, this is the line which is for this ratio equal to 1. Now this is the line which is for this ratio, which is r equal to 1. And then we have one more point over here which is as such of no any importance as of now. You won't be able to appreciate it, but we'll try to see to it afterwards. Okay, so this is square root of 2. Okay, now let's try to see what happens when r is very small, that is when r is equal to 0, or r tends to 0. See, when r is 0, this numerator itself comes out to be 0, which essentially means that there won't be any vibrations when r is equal to 0, which is obviously anticipated. Because why vibrations are coming? Vibrations are coming because there is that rotating unbalanced mass in it. Okay, so when r will be equal to 0, which essentially means that mass is not rotating. So even if it is not balanced, it is not rotating. So that's why it is not going to cause any time varying force acting onto it, and obviously you are not going to see any vibration of that capital M. Okay, so total mass m will not vibrate at all. Okay, its amplitude will always be equal to 0. Okay, so we are going to start from here. Okay, let's consider that case where xi is equal to 0. Okay, in the typical fashion that we do, we always start with that case where xi is equal to 0, that is undamped case. Now in that undamped case, xi will be 0 when xi is 0, and when r is 0, we are starting from here. Now as r builds up, you get to see such kind of behavior, and then the resonance, which tells us that amplitude will be equal to infinite. You put r equal to 1 and you will get to see that xi 0 and r1. Okay, so xi 0, which essentially means that this term is absent when xi is 0, and this is the term which is going to give you this infinite amplitude. Okay, now if you further increase r, what will happen is that it will come down from this infinity. Okay, now resonance has you have surpassed that resonance value, and you are ahead of omega, your omega is ahead of omega n. Now in that case, this value will drop down. Okay, and it will reach 1 in the asymptotic fashion. This is what is the curve for xi equal to 0. Now if you increase xi further, then you get to see such kind of curve. Even further, something like this. And then after certain time, you are going to see such kind of behavior. Okay, so where, I'm so sorry. Yeah, so yes, So what we were discussing is that, yes, so these are the curves for increasing value of xi. Okay, so as xi increases, you move towards over here. Okay, and this is the curve for xi equal to 1. Okay. So for certain values of xi, after certain value of xi, which one is that we are going to see just now. Okay, so after that you shift over here on the other side of this line, which is for this ratio equal to 1, and then you get to see such kind of behavior. Okay, what is the meaning of these curves? So this curves tells us that for smaller values of xi, okay, in most of the cases, when let's say we consider that case where xi is equal to 0. Okay, so once you are ahead of this r, okay, so once the frequency of rotation is larger than this value, okay, then in any case this ratio, which is capital Mx divided by Me, that ratio will always be greater than 1. This not r, that this particular value capital Mx divided by small me, that will always be greater than 1 once r is larger than this. Okay, it builds up steadily, it goes to infinity at the resonance, again drops down, and with increasing value of r it reaches to value equal to 1. Okay, so in the approximate sense it is 1. Okay, and it will be exactly 1 when this r will be equal to infinity. So for very larger values of r, this ratio is 1. Okay, so because of this unbalanced mass, okay, so whatever me that is there, so how much unbalance is there and how far it is there with respect to that axis of rotation. So because of that, what is happening to the system is vibrating, and system is vibrating with amplitude x, and in such a way that capital M times x is exactly equal to me for higher values of r. Okay, however, you need to appreciate this capital M is the total mass of machine, and the small m is the unbalanced mass. Okay, total mass of machine is in general pretty large as compared to the small m. So obviously this x comes out to be fairly small in comparison with E. Okay, so we try to ensure that most of the rotating mass is balanced. Okay, so even if there is some unbalance, let it be very small unbalance. So if that unbalanced mass is very small in comparison with the total mass of the system, then in that case the amplitude of vibrations of this mass will be fairly small. Okay, because this ratio is 1, and if this m, capital M, is much larger than small m, then obviously capital X will be much smaller than this E. And we also try to see that the unbalance is not much away from the rotating axis of rotation. Okay, so so you might have experienced it while operating washing machine, that if a large load is unbalanced, then you get to see larger amplitudes. Okay, that is because this, in that case, this capital M also, the small m also becomes fairly large. Okay, and hence this capital X becomes fairly large. Okay, now we have now seen that graph which is for xi equal to 0. So for when we increase xi further, that is when xi is greater than 0, larger than 0, in that case you never see infinity amplitude at resonance. Okay, so when omega will be equal to omega n, you won't ever see large amplitudes, or rather infinity amplitudes. There will be certain I mean amplitudes will be fairly large, but it won't be equal to infinity. Okay, no, so now we are clearly able to observe over here that there is a maximum at certain location. Okay, now where that maxima is going to occur, we are going to carry out the same process that we already have done before. So what we'll be doing is, we'll be differentiating that ratio with respect to r, the ratio that we are plotting, which is capital M times capital M x divided by small m times small e. We'll be differentiating this ratio, expression of this ratio, whatever that we have obtained, which is this one, Okay, so we'll be differentiating this expression with respect to r, and that derivative we are going to equate to 0, and whatever comes out because of that, that will give us where exactly we get to see the maxima, and we'll be able to see that maxima occurs. You can derive it by yourself and try to check it out. So maxima occurs at this location, okay, for this value of r, which is equal to 1 over under root 1 minus xi 2 xi square. It is, I'm so sorry, so it is 2 xi square. Okay, so you put value of xi in this one, and you are going to see where at what r you get to see maximum amplitude. Okay, so depending on value of xi, where maxima is going to occur, for what value of xi maxima is going to occur, that is going to change. And one important thing is that you will get to see maxima only till that time when xi will be smaller than 1 over root 2. Okay, thereafter you are not going to get a real number coming out of it. Okay, so when xi is greater than 1 over square root 2, this term will be smaller, this term will be larger than 1, and hence it will be negative, and it is in this sign, which is this under root sign. So because of that, you are going to take a square root of that negative term, which will come out to be an imaginary value, and obviously you cannot have imaginary omega, right? So there it won't exist at all over there. So the existence of maxima is only till this condition, till the time xi is smaller than square root of 2. Okay, so when xi is smaller than square root of 2, you get to see that there is a maxima somewhere over here, and obviously for all values of xi, these curves end in 1. Okay, so for increasing xi, they are reaching over here towards 1. So which essentially means that for xi smaller than 1 over square root of 2, you are going to see a value which will be larger than 1 somewhere, right? So for all those values of xi which are smaller than 1 over square root of 2, graph will cross in this fashion. They will be larger than 1 at certain location, and then it will reach to 1 in this fashion from the top side, whereas otherwise it will reach over here to that 1 value from the bottom side of this line, right? It will approach in this fashion. Okay, so this is what is the this is what is the set of curves that we have plotted. And one more point that I want to tell you, that okay, so this is so what we have obtained, that this is the value of r for which the maxima occurs, but we also need to need to know that what is the amplitude at that location where maxima is there. Okay, so what is the maximum amplitude, that also you can derive. What you have to do is you have to put this expression of r in the this expression. Okay, if you put that value of r over there, then you will get to see that capital M x divided by small m e maximum. Okay, this is the maximum that you can get, that will be equal to 1 over 2 xi into 1 minus xi square. Okay, this is that maximum amplitude. Okay, and it occurs for this value of r. Okay, and you will be able to see that it occurs only till that time when xi is smaller than 1 over square root of 2. Okay, so with this we'll stop on this front, and we'll be meeting with a new topic in the next class. Okay, thank you so much.